Welcome everyone to this third video about the best methods to prepare ketones from amides. This presentation is about the acylation of carbon nucleophiles by amides under acidic conditions. This includes the famous Wilsmeyer formulation, but other amides than DMF and other activating reagents than phosphorus oxychloride can also be used. The preparation of aromatic aldehydes by electrophilic aromatic substitution with formamides is of course particularly valuable, because the only alternative is the unwieldy mixture of carbon monoxide and hydrogen chloride in the so-called Gattermann-Koch reaction. Formyl chloride is not stable, and formic acid esters will often alkylate an arene instead of formylating it. Acylation with amides under acidic conditions can, however, also be used to acylate amides, ketones, and other carbon nucleophiles in a simple way, without the need of high dilution or low temperature. These reactions are therefore easier to scale up than enolate chemistry. For large-scale industrial preparations, phosphorus oxychloride can often be replaced by phosgene or mixtures of phosgene and aluminum chloride. I've sketched here the idealized mechanism of a hypothetical Lewis acid-catalyzed acylation of propene with an acetamide. In most of the examples I'll show you later, the amides were activated by conversion into a chloroiminium chloride by treatment with phosphorus oxychloride or phosgene. The mechanism of these reactions is analogous to the one shown here, the only difference being that the Lewis acid oxygen adduct is replaced by a chlorine atom. Formation of the new carbon-carbon bond from the activated amide and propene yields a hemiaminal. This intermediate will always be cationic because amino groups in hemiaminals are only slightly less basic than tertiary amines. Elimination of the ammonium salt then yields the ketone. Unfortunately, also ketones will be activated by many acids and can react with the nucleophile to yield a tertiary alcohol. This alcohol may even react a third time with the nucleophile or undergo elimination. So, one critical issue of these reactions is how to stop them at the right time. The most common nucleophiles used in acid-mediated acylations with amides are electron-rich arenes and heteroarenes. The reactions can proceed intermolecularly or intramolecularly. With alpha-beta unsaturated amides, annulation reactions can occur and yield indanones. Examples of the isomerization of anylides to aminoaryl ketones have also been reported. Also, enolizable ketones and related compounds can be acylated by amides. Then, electron-rich alkenes such as silyl enol ethers, enamines or ketene acetals do also react with sufficiently activated amides. I'll show you some examples in a minute. This here is an example of the acylation of dimethylaniline with an anilide and phosphorus oxychloride as activator. Interestingly, no acetylation by or freeze rearrangement of the aryl ester occurred, and the non-methylated aniline remained unchanged. The target benzophenone was obtained in moderate yield, despite the many potential side reactions. Also in this example, a benzophenone was prepared, but instead of aniline, 4-nitroaniline was used as leaving group. Nitroanilines are more difficult to acylate than non-deactivated anilines and less likely to compete with the nucleophile. Here, the acylation was catalyzed by an excess of triflic acid, which could be recovered by distillation. Sometimes it is even possible to catalyze such acylations by sulfuric acid without much competing electrophilic sulfonation. In this example, the use of concentrated sulfuric acid gave a high yield of fluorenone, but when the acid was too dilute, only hydrolysis of the amide occurred. In this example, an optimized Wilsmeyer formulation was conducted with phosgene and aluminum chloride as activators. Only a slight excess of DMF and a small amount of chloroform were required, and 90% of the target benzaldehyde along with 4% of the ortho isomer were obtained. Unfortunately, Wilsmeyer formulations only work really well with electron-rich arenes or heteroarenes, but with less activated arenes yields are often much lower. Formulation of these weaker nucleophiles are sometimes more successful with dichloromethyl ethers as electrophile instead of DMF. Like Friedel-Crafts acylations, Vilsmeier formulations usually stop after the first formulation because the formyl group strongly deactivates the arene. Occasionally though, with very electron-rich arenes, twofold formulations can occur, as in this example. Thiophene is already electron-rich, and aminothiophenes therefore exceedingly nucleophilic, what explains the high yield of diformylated product. I would expect the starting material of this reaction to be quite unstable and quickly oligomerize in the presence of air. This is an example of cyclopentanone synthesis by acylation and alkylation of thiophene with an acrylate. As activator, triflic anhydride was used. The low yield may have been due to intermolecular reaction of the first intermediate with the second molecule of thiophene. This side reaction may have been avoided by diluting the reaction mixture even further, but this is not always practical. In this example, a diacylated aniline was isomerized by heating with an excess of aluminum chloride, without any solvent. A freeze-like rearrangement occurred and mainly the para isomer was formed. Treatment of ketones with the Vilsmeier reagent, that is, with the chloroiminium chloride prepared from DMF and phosphorus oxychloride, can cause alpha formylation and then deoxychlorination of the ketone. Methyl ketones may be formulated twice at the same methyl group or at both alpha positions, as in this example. Here, benzofuranone was acylated with the 4-nitrobenzamide. The intermediate diketone was then deoxychlorinated by the excess phosphorus oxychloride to yield mostly the isomer shown. As discussed in part 2 of this playlist, amides are often too unreactive to undergo condensation with amide enolates. Thus, treatment of the starting pyrrolidone of this example with a strong base will probably not give a high yield of the dimerized amide. With phosgene or phosphorus oxychloride, however, such dimerization can proceed smoothly. Here, phosgene was used, and the target condensation product was obtained in 68% yield. Acyl chlorides with alpha hydrogen readily enolize, in particular if they contain additional electron-withdrawing groups. Such acyl chlorides can therefore also react with activated amides, as in this example. Here, the intermediate acyl chloride was formulated twice and then probably underwent hydrolysis and decarboxylation during the aqueous workup. Electron-rich alkenes, such as silyl enol ethers or enamines, do also react with chloroiminium chlorides, as in this example. The reaction already proceeded at room temperature, and a high yield of alpha-formyl cyclohexanone was obtained. Such alpha formulations can be used to temporarily enhance the acidity of a ketone, for instance for a diazo group transfer, a Yap-Klingemann reaction with an aryl diazonium salt, or for a Michael addition. During such reactions, the formyl group is usually cleaved off again. Formyl ketones are also suitable starting materials for the preparation of pyrazoles and isoxazoles. This is an example of the formulation of an enamine, again to prepare 2-formyl cyclohexanone. Here phosgene was used to convert DMF into the chloroiminium chloride. Let's now have a look at potential side reactions. As already mentioned while discussing the mechanism, under acidic conditions also ketones or aldehydes can react with a given nucleophile. In the case of an arene acylation, this would cause the formation of diaryl methanols or triaryl methanes, as in this example. Here, an excess of substituted aniline was used as nucleophile, what led to the formation of a triaryl methane or a benzhydrylamine, depending on the precise substitution pattern of the aniline. During formulations with DMF, products are occasionally reduced by hydride transfer. Here, for instance, when N-ethylcarbazole was treated with an excess of Vilsmeier reagent, a small amount of benzhydrol was formed, which was then reduced to a diaryl methane. Formic acid derivatives can deliver hydride, and I've sketched here 2 potential intermediates that could have been the source of hydride here. When NN-dialkyl anilines are acylated by activated amides, one type of byproduct can result from hydride abstraction from the alkyl groups. In fact, 2-dialkylaminobenzylaldehydes or phenylketones can be reduced to alcohols just by heating, by intramolecular hydride transfer from the nitrogen-bound alkyl groups. In this example, this side reaction became the main reaction pathway. Then, primary amides may not be activated but just dehydrated to nitriles by the typical activating reagents, as in this example. No intermolecular acylation of the arene occurred, despite being electron-rich. The mild conditions and short reaction time may have contributed to this result. On this and the next slide there are some more examples, which you can also find in the description of this video. This was the last video of this playlist. In my channel you can also find video playlists about the conversion of other carboxylic acid derivatives into ketones, for instance esters or acyl chlorides, including a thorough discussion of the Friedel-Crafts acylation.